Hi, welcome. My name is Michael, and the title of our work is Towards Improving Code Stylometry Analysis in Underground Forums. So, how will we tell who wrote a piece of text? Well, we would use something called stylometric analysis, which is the study of writing style. And in order to do this, we need to extract features from the piece of text that would enable us to capture the artifacts of the writing style. And then, in the state of the art, we would use machine learning algorithms to train a model, give it samples from lots of different authors, and then when giving a new sample, a new unseen sample to the classifier, it should be able to tell us who wrote it. This is the authorship attribution problem. And so, in the literature, these techniques are evaluated using for example, the Google Code Jam contest code, a very popular dataset, and it comes from the Google Code Jam contest hosted by Google, where programmers sign up and they solve a set of programming problems and submit their solutions. Also, there's been work using code scraped from GitHub repositories. That's also been used to evaluate these kinds of tools, but we wanted an even more organic environment, and for that we wanted to see what would happen if we applied these techniques to code gathered from underground forums. Underground forums are places on the internet where malicious actors gather to buy and sell illicit products, including narcotics and malware as well, and they also share source code with one another. And learn from each other on how to write malware. And so, when applying these state-of-the-art techniques using a random forest classifier, we get the following, where using the Google Code Jam contest code, we get very high accuracies across the board from 20 authors to 100 authors. We get very accurate authorship attribution. When performing on GitHub repository code, there is a marked degradation in performance, but when applying these same techniques to code gathered from underground forums, the results are even worse, ranging from 66% accuracy with 20 authors to half that with 100 authors. And so the first contribution that we present is we show that the state-of-the-art in code stylometry techniques do not work well for code shared in underground forums. And well, why is that? What's the problem? Well, Google Code Jam contest code has properties to it that are not present in more organic environments. So for example, the code samples tend to be very long. The ground truth of authorship of each sample is pretty much guaranteed, as people will get disqualified if they plagiarize. The samples are guaranteed to compile. There's no exotic libraries being used because these contests are about more logical puzzles than software engineering problems. And there's a very limited scope of problems that are solved. So everyone solves the same set of, say, 10 problems in 1 year. So the second contribution that we want to present is that we designed a methodology aimed at improving code stylometry authorship attribution in underground forums. And we use conformal prediction to inform our confidence thresholding, which is one of the steps of our methodology. And so this is your standard machine learning pipeline, if you will, for authorship attribution. You want to get your samples, you want to extract abstract syntax trees from them, and then extract features from both the abstract syntax trees and the raw code itself. Train a random forest classifier model, for example, perform your classification, and from that get your authorship attribution labels. And so our first addition to this pipeline, the first step of our methodology, is granularity selection. So what that is when we scrape a source code file from these forums, we split it up into its constituent functions. and we treat those as separate samples. Secondly, the second step is code clone removal. So if we have duplicates, if we have duplicate functions, for example, author A and author B has submitted the same function, has posted it, then we remove both of those samples, as we say that we cannot guarantee ground truth in this case. So we reject both. Thirdly, we have the sample pruning step, whose goal is to simply discard any sample that is not informative enough to be helpful in our classifications. So, for example, samples shorter than 25 characters long will be discarded. Then, after the training and classification phases, the fourth step of our methodology is confidence thresholding, in which we reject samples which are judged to be too uncertain. And for this we use the conformal predictor to give us these confidences that we can then use to either reject or keep a sample. And the fifth and final step of our methodology is function majority voting. So, for example, if author A has if a specific source code file was split up into 5 constituent functions, and 4 of those functions are classified as author A, but 1 of them is classified as author B, then we would give all 5 the label of author A, because most of them were classified as author A. And then from this we get our authorship labels. And so the third contribution is that we show the benefits of applying our methodology both in a closed world setting and an open world setting. So very briefly, a closed world setting is one in which the classifier knows all of the authors in the testing set. So you give it samples from a set of authors which it trains on, and then every sample that you give it in the testing set, it will belong to one of those authors that it has already seen in the training set. Whereas in the open world setting, this is not necessarily the case. So you give it samples from a set of authors to train on, but in the testing set you will give it samples that do not belong to necessarily any of the authors it has seen in the training set. And so for the closed world, we evaluate on 20, 50 and 100 authors in line with the literature, on code gathered from underground forums, GitHub repositories and the Google Code Jam contest. We apply our methodology and see the results. And so here are the results. We can see that our methodology results in performance improvement across the board, but especially in the setting in underground forums with 100 authors, where the performance goes from 33% to 77% post methodology, more than doubling the performance. For the open world setting, we take 100 authors and we label 20 of them as in-world and 80 of them as out-of-world. And we compare the confidence thresholding with 2 different confidence metrics. One is provided by the random forest classifier itself, is the probability that it gives of a certain prediction, and the other is using the conformal predictor. And so this is kind of a complicated graph, but what it shows is how many of the in-world authors you retain as you vary the confidence threshold of keeping samples. And so with the conformal predictor, we retain 11 authors while achieving 100% in attribution accuracy when we tell the conformal predictor to keep all samples at a confidence of 90% or thereabouts. Whereas at a comparable accuracy with the random forest classifier, we only retain 1 author, and so it has a tendency to reject more in-world authors than the conformal predictor, even when achieving similar performance. And so by this we show that the conformal predictor is giving a better trade-off of rejecting out-of-world samples. So in summary then, the challenges with authorship attribution are that there's not enough data really per author and per sample in these more organic domains to perform proper analysis, to get these results as you do with curated datasets like the Google CodeJump dataset. And classifiers rely more on lexical features rather than higher level syntactical features. So the classifiers will learn more on the context of the code itself rather than the writing style of the author. And so the lessons learned here are that we need more capable fuzzy parsers first of all, because a lot of the samples that we gathered from these underground forums, they were unusable because you couldn't extract any syntactical information from them because they could not be parsed. Function level granularity is very important, and this leads into function-wise voting mechanisms, which is the step in our methodology that actually improved the results the most. The effect of plagiarism is quite small, so the code clone removal step actually resulted in the smallest performance improvement. And the importance of context of code. So the classifiers tend to learn on the context the code is in again, rather than the writing style. And so if you're interested, all the code is at this GitHub repository that we have used for our experiments, and that's my contact email if you have any questions. Thank you.